So first of all, I want to thank the organizers for inviting me. I don't really feel so my intersection with cluster algebras is a little bit like Harold's. I use it, and then I don't know how much I contribute to the theory of cluster algebras, but at least cluster algebras contribute something to the theory of representations. Okay, so I'll go over some history. So I've been talking about the same subject for a while, so I'll go over some history about this, and I'll talk about the the Q system, which, as David said, is a reduction of this system, but not quite, and it's quantization, which is not this quantization. And then I'll talk about how specifically, explicitly, you see the quantum affine algebras appearing from the quantum Q system. And then I will T-deform everything. So we'll get into McDonald theory and other quantum Q systems and see how cluster algebras enter there. Okay, so the history goes like this. So I started by looking at what I call fermionic character formulas for the tensor products of KR modules. So David already told you that there were such things as KR modules. So they look like this. So there's some special nice modules of, say, the quantum affine algebras. And you take tensor products of them, and they appear in statistical mechanics. And from statistical mechanics and from Bethe-Ansatz, there was a conjecture for some explicit, combinatorial, absolutely explicit formulas for the decomposition of these tensor products into irreducible components. And then my other entry into this is that Fagan and Lucht have defined the notion of fusion product, which is, I think, what Harold was writing as star. I think eventually. And I'm not going to really define this. I've talked about this many times, but I want to say that it's not the representation theory of quantum affine algebras, it's the representation theory of, okay, this is not working, of affine algebras instead. Then, Kirillov and Reshetikin and the Japanese group that I will name presently, they knew about the very close relation between these formulas and something called Q systems. And this is where Q systems were first written down in the 80s. And then where I enter into this and where cluster algebras enter into this is that we recognized that the Q system was a cluster algebra exchange relation, that there was a Laurent property, and that this implied some proofs about the conjectures. So there were conjectures for these fermionic formulas, and we use this to prove these conjectures. So everything in this picture is proven. And then I want to Q-deform everything. So Q-deformation in this language, well, I think it's the same as Harold's language. Fagan and Lucht have actually defined graded characters, not just characters, of tensor products. And then there's a fermionic formula which is graded, also with an energy function that comes from statistical mechanics, or a grading that comes from statistical mechanics. And the next contribution of cluster algebras is that given a Q system, as Harold wrote down, there's the obvious quantization. So the natural quantization as a cluster algebra, you get a quantum Q system. And so just to make a distinction, it is not this. Not what you get by doing this. So I want to make clear it's not the same quantum cluster algebra. And what we showed with Di Francesco is that this quantum Q system is in fact responsible for the grading of the fermionic formulas. So it seems like the grading comes from the quantum affine, from the affine algebra in one place. It comes from the statistical mechanics, or quantum affine algebras, or crystals, in the second line. It comes from the Q in quantum cluster algebras in the third line. And then again, we can use the Laurent property to prove all the theorems in there. Okay, so that's the history. And then what's not history is that I want to understand what is this quantum Q system in an algebraic sense instead of a geometric sense as Harold did. So I became curious about what exactly is happening here. And this is I think the right-hand side of your Setake correspondence, but I didn't know that, so Okay, that's my history. I'm going to concentrate on these two middle lines for this talk. You have a pointer.
You have to use both, I'm sorry.
I have to use both. It's a bit silly. Okay, all right, fine. Which one is? Oh yeah, okay. So I'm going to mainly concentrate on the red part. My hands are full now. Okay. I have to remember which one. Okay, so I start here. So Q systems, and I'm going to define an algebra AG, and I'm going to study this algebra AG and its deformations. That's what I wanted to say. If you didn't know about the history, this is enough for you. So for any simple Lie algebra, I'm going to define an algebra AG. Oops. Oh. I'll get it by the end of the talk. So the algebra AG is a commutative algebra, and it's generated by elements Q, A, K, and A is a root. So you take any simple Lie algebra, you take the dinking labels. So A is a dinking label, and K is any element in any integer. So you take the polynomial algebra and modulo the ideal generated by these relations, where K is some monomial. So these relations are closely related to David's relations, but not quite. Okay, there's a minus sign here. And, okay, I can renormalize this minus sign away. It's not important for me. And K is a monomial. And for example, and I'm only going to consider the classical types, A, B, C, D in this talk. So for example, for the classical types, so if the algebra is simply laced, K is just, whenever C is connected to B in the dinking diagram, it's the product of C's connected to it. And for the BC types, this is K, okay. Whenever you have this arrangement, you have this monomial, and whenever you have this arrangement, you have this monomial. I don't know if you can actually see. Okay, so these systems were written down by Kirillov and Reshetykhin, and then next by Kundiba, Nakanishi, and Suzuki generalized them for all types. So they knew they had something to do with representation theory of something, but it was a long slog. So the representation theory connection is that if you define these W's that are conveniently written down here, they're special modules, so let's just call them Kirillov-Reshetykhin modules and not worry about how to define them. They carry a spectral parameter zeta, and A, which is a dinking label, and K, which is an integer. So it's a finite dimensional representation of an infinite dimensional algebra, and this infinite dimensional algebra can be the quantum affine algebra as discussed by David, or the current algebra, which I prefer to discuss, or the Yangian. And then I consider its restriction to the finite dimensional part. So for example, if I consider the current algebra, G is inside the current algebra, I consider the restriction of this module W to G, and that doesn't see the spectral parameter. So I ignore the spectral parameter when I do this restriction, and I call the character of the restriction Q. And that's suggestive notation because the theorem, which was, I think Kirillov-Reshetykhin knew this for type A, maybe. Nakajima proved it for types, for the simply laced types, and Hernandez proved it for all other types. Characters of KR modules satisfy the Q system after, okay, I evaluate, and I'm going to draw a lattice here. So suppose I'm doing type. Okay, suppose I have an algebra of rank R, so 1, 2, 3, 4, R. And then K equals 0, 1, minus 1, okay? So this is a strip in the lattice that goes on forever in both directions. Does everybody see the lattice? Good. Okay. These would correspond to characters of the trivial representation, and if you evaluate them to be 1, the structure of the Q system tells you that as a result. These, for example, so these are 1, these are going to be 0. So this is a quotient. I'm taking a specialization. These are going to be called what are known as the fundamental KR characters, these guys. Okay. So if you do this specialization, then the characters of KR modules satisfy the Q system. So the Grothendieck ring of G is somehow oops. No? You don't want to go? Okay. The quotient of AG by this ideal that I get by this specialization is, the quotient of AG is the Grothendieck ring. And the ring is generated by this particular column, which are called the fundamental characters, like you would expect for regular representation theory. Any questions? It's difficult to talk and at the same time. Okay, so consequently, any QAK under this specialization is a polynomial because it's in the Grothendieck ring, and the Grothendieck ring is a ring in the fundamental characters. But also there's a cluster algebra connection, which we heard about before. So AG is a subalgebra in the cluster algebra, and with this exchange matrix, and I'm going to consider the non-simply laced cases as well. So this is my exchange matrix, and I'm not going to draw Harold's pretty pictures for this exchange matrix, but you just take the dinking diagram of your algebra, and then you box it with SL2 hat diagram, and I think that's about it. So for the cluster seed, which consists of, say, these two columns. So it's a cluster algebra of rank 2R with this exchange matrix. So this is something that when I met Zielewiński for the first time, I was sent to him in order to, because I was asking about this polynomiality property, and he helped me understand that the Q system was actually a mutation in the cluster algebra, and that's where my connection to cluster algebras began. So I'm very grateful for that introduction that I got. Okay. Okay. If I press enough buttons. Okay. So the fact that and this is, I should thank Sergei Fomin to helping me to understand this as well. The fact that QAK is a polynomial, once you take the quotient by the relation that this column should be all ones, the fact that QAK is a polynomial, in fact, all cluster variables in the larger cluster algebra are polynomials in the QB1. In these variables, that is, the variables that go in this column, is just a consequence of the Laurent property of cluster algebras. Okay, so that's part of the history of this. Okay, so I'm not going to take the quotient anymore. I want to talk about tensor products and the fermionic character formula. And so let me not define what a fusion product is, but essentially if you have a finite sequence of finite dimensional modules, if you take their tensor product, you can define the tensor product, you can define an action. So you take G modules, you take some G modules, you extend them to G of T modules. You can define an action of G of T on a G module simply by some evaluation. And if you want to, you can define an action on the tensor product and then take the associated graded space. And this is essentially the Fagen-Luchtov fusion product. But all it is it says that this F star is a G module with graded components, and each of the graded components is a G module. And then they made some conjectures about this. So the first conjecture that they made was that once you take the associated graded space, the dimension doesn't jump. That is, the dimension of the tensor product is the dimension of their fusion product. And this is not true. But it's true if all the representations are KR modules, or restrictions of KR modules. Okay, so we proved this mostly in the work with Eddie Ardon in 2006, and then with Di Francesco in 2008, again using this polynomiality property.
So you, by construction as a vector space, that isomorphism is always true?
This isomorphism is not always true.
So what's the underlying vector space of F star vi then?
So this is a graded space, but if I don't look at the grading, if I just look at the G module structure, the conjecture was that it should be isomorphic as a G module to the tensor product. That is, when you take the associated graded space, you don't lose any information. But it's only true for special kinds of modules.
But is it true that the underlying vector space of F star is just this tensor product of the VI's, or even that is?
No, it's not true.
Just separate.
The dimensions are different. I mean, in general, it's not true. So, but it is true if these are KR modules. I mean, there are counterexamples. Okay. All right. And then the second conjecture had to do with, you have a grading for this fusion product. So if you take the characters associated with this grading, so these are just polynomials. So by character of F star sub z, I just mean the symmetric function, which is the character of the G module, F star. So you consider F star, the graded component, the nth graded component, as a G module, and you take its character as a G module. So this is some symmetric, W symmetric polynomial in Z, the variable Z, Z1 through ZR, or Zn. And then I form a generating function for the character of this space. So Q is it keeps track of the graded component. Okay, so if all the modules are KR modules, so this are KR modules, then we use the explicit fermionic sum formulas from Kirlover-Shetikin and Hatayama Kuniba Okado Tsuboi Yamada. It's been a while since I've done that. Did I do it right? So they wrote down characters using, the beta ansatz. And so there are some formulas. We call these formulas M, and they depend on V of Q. Q is this Q in the grading, and Z is this, the weights of the algebra. And that was the second Fagan-Loktev conjecture, that their character, this graded character, should be equal to these fermionic sums. Okay, so we proved that. But what I want to say is, so far, the proof just goes via the classical Q system. It was enough to prove it for Q equals 1 and use positivity to show that it was true in general. The property of these fermionic character formulas is that they're positive sums. They're always positive, just like the polynomials that David was talking about. Any questions? I lost everyone. Okay, so then, okay, I have a cluster algebra and I want to quantize it. And so I go ahead and do that. So I quantize the cluster algebra and I look at my subalgebra, which corresponds to AG. So it's the subalgebra generated by the same generators, which are now curly Q. I don't know if you noticed that they switched from being Roman Q to curly Q. And those are my quantum generators. They're non-commutative generators, and I consider the universal enveloping algebra of those generators. And they satisfy the relations that I get from the cluster algebra. Those are the relations, I claim those are the relations that I get from the cluster algebra. So they're slightly simpler than what you would get for a generic quantization, and they're simpler because of the special form of my B matrix, my exchange matrix. Here, lambda is essentially the inverse of the Cartan matrix. And I use V and not Q because I've already used Q in this talk, and this V is not equal to Q. And, okay, in general, for any, so this is the exchange relation, the quantized exchange relation in general for any G. So, oh yes, I have to define what I mean by ... K. That's physics notation for normal ordering. And it just means that if I know that the elements in the monomial K, if the elements that make up this monomial, if they V commute in some sense, then the ... product is just this thing. And actually, if it's already implied in Bernstein-Zelevinsky's paper, such a ... product. So it's physics shorthand for what they wrote down. Okay. Any questions? Okay. All right. So here's the theorem. So with Di Francesca, we wrote down this theorem in 2011, and my student Simon Lin has just completed the proof for all other G's. So there is a linear functional between the ordered product. So so I have an ordered product here, a monomial. These elements are in different clusters. Okay, so it's not a cluster monomial, but it's an ordered product of these generators Q, A, K to the power N, A, K. So this N just keeps track of how many Q's I have, and I hope that I have a finite number of N's that are non-zero. So there's a linear functional that sends this order product, so it's some sort of expectation value, it's a matrix element, to my characters. So this is an element in my cluster algebra, and I managed to get some function out of it, which is a series in Q, which is W symmetric in Z. And so I'm not going to write down this linear functional, I'm just going to say that it exists for now. Okay, and the identification is here. Q is v to the minus delta, well, delta is the determinant of the Cartan matrix. Obviously not 0. Okay, so I've talked about this before because it's kind of an old paper. The only new thing is the generalization by my student to other types. Very technical proof. Okay, so the quantization of the quantum Q system cluster algebra defines a quantum Grothendieck ring. And this quantum Grothendieck ring is the one that's compatible with the Fagan-Luchte fusion product, and I believe the one that's compatible with Herold's tensor products, or whatever you want. What did you call them? Convolution products, yes. So this is a completely combinatorial way of defining this. Oh, any questions? So this is my way of defining the deformed Grothendieck ring. Okay. So now I want to understand this algebra. So, yeah.
So does the Fagan-Luchte product implicitly define the deformed Grothendieck ring, or that's on its own?
No, because the Fagan-Luchte product is commutative. So it's sort of the image that we see on the level of characters, that if we had a non-commutative product, this is what we would get for the character. So this linear functional, I think maybe you've seen this before, but this linear functional involves the fact that, okay, this is a quantum cluster algebra. You can express everything in terms of initial data variables. You take a constant term and, you normal order them. You take a constant term in Q1, okay, and you get a series or a polynomial. There is no reason I know why the Fagan-Luchte product should be compatible with this. I believe they knew about your picture, though, when they defined it. So somewhere in Fagan's head is hidden the reason for this, but I don't know what that reason is. Okay. This was working before. I'm sure about that. Okay. So I now want to look at the other side of this correspondence that Herold wrote down. I want to understand this algebra AG, curly AG, so that's the non-commutative algebra generated by my elements Q, A, K, by this lattice, by the elements of my lattice. Okay? So it turns out this is a really nice algebra, and then I didn't say anything about the quantum Q system. It's a discrete integrable system. Integrable systems are behind all of this. Toda Q systems, all of this. They're behind all of this, and we use this fact to prove a relation to quantum affine algebra, and then to DAHA even. And what I want to say is that now I'm going to give you the answers in type A, and I'm going to say that there are answers in types B, C, D, and I'll give you a hint of what those answers are, and I'll make an advertisement. Okay, so let's go back to the quantum Q system, and in the quantum Q system, I don't write it that way, but my... No, I'm just looking for this. So I start out with this initial data, and I can evolve in this direction or this direction using cluster mutations. That's this Q system, okay? K is this direction, right? K. Okay? Because it's a cluster algebra, I know that all elements of AG are Laurent polynomials in initial data, for example, these two columns. Because they generate, that's enough initial data for my mutations. And then, I didn't say this is R, but you know, I can continue this lattice and just write my equation. So I'm writing down the equation for type A. What is Q0K? So I'm just using notation, Q0K is 1. So here and here, I just have 1s. And that's a notation. It's only a notation. There's nothing special about this. Now, I want to understand AG as a polynomial algebra, not as a Laurent polynomial algebra. And these elements in these two columns, they don't generate A as a polynomial algebra. They generate it as a Laurent polynomial algebra. So I'm going to, what I call, rotate the quantum Q system. That is, I'm going to start with this as initial data. In the classical case, it doesn't matter. I can do whatever I want and mutate in this way, or maybe in the other direction. This was R. Okay, maybe mutate this way. Yeah.
Now you're taking an infinite amount of...
I'm taking an infinite number of generators A prior I. So A prior I, I'm gaining something in that I have a polynomial algebra, but I'm losing something in that I have an infinite number of generators. So I will address this. Okay, so this is why I call this a rotated quantum Q system. I just took one term and put it on the other side. Okay, so I'm mutating in A. Okay, so it's a different cluster algebra, infinite rank cluster algebra. Okay, and now when I say Q0A, K is equal to 1, that's now a boundary condition, not a notation. And QR plus 1K is equal to 1, that's a boundary condition, or initial data and boundary condition, instead of being a notation. So I'm just turning my head and looking at things differently. Okay, so it defines a cluster algebra of infinite rank. And using the same argument that Fomin indicated for when you put in the sort of K, the boundary condition that these are equal to 1, everything else is a polynomial, I can say, okay, I have a boundary condition, all of these are equal to 1, everything else is a polynomial. So if you're familiar with that argument, you're familiar with that argument, and if you're not, you just have to believe that because of the level of symmetry of this algebra, it's true. In fact, I know what those polynomials are. They're just determinants. So because of, if you look at this equation, does any of these work now? This vaguely works. If you look at this equation, you can reinterpret it as an equation for determinants, and there's a de Nano-Jacobi relation. And in fact, say Q2K is just the determinant of the matrix QK, QK, QK plus 1, QK minus 1. Okay, and so on. They get larger and larger. Okay, so we know one polynomial form. Of course, there isn't a unique polynomial form because we have cluster algebra mutation relations. Okay. Okay, so the theorem is that the algebra AG is equivalent to a polynomial algebra generated by this top line, by this bottom line, with this boundary condition that the R plus first determinant is 1, which is equivalent to the R plus second determinant is 0. Okay, so now I have, it looks like we traded a finitely generated algebra into our elements and their inverses for an infinite number of generators, but now I have the fact that the Q system is an integrable, discrete integrable system, and it has conserved quantities. It has, in general, R plus 1 conserved quantities, which are, if you take the determinant, let me just make this determinant slightly larger so you can see the pattern. QK plus 2, QK, QK plus 1. So this is Q3K, QK minus 2, QK plus 1. Q3K for SL2 is going to be equal to 0. that means that I can expand this determinant in the top row. These are the Q1Ks. And I get a linear recursion relation between QK plus 1, Q plus a 3-term linear recursion relation. And theorem, the coefficients are independent of K. And the coefficients, the only non-trivial one is the determinant of this matrix, is independent of K. That's the theorem. It's a conserved quantity for SL2. And in general, I can repeat this argument for SLR, right? SLR plus 1. So in general, I can reduce my number of generators to 2R plus 1 using this. That is, because I have a linear recursion relation, I can relate QK plus 2 to the other variables in this matrix via the linear recursion relation. And so once I have the 2R plus 1 generators, the next generators is determined by this linear recursion relation. So in fact, it's finitely generated. So okay, that has to do with the fact that it's a... How long do I have? Good Lord. Okay, I'm going to start talking faster. Rotating the quantum Q system, I can do the very same thing, but I have to take the quantum Q system that I wrote down. And now this relation is not a mutation in the quantum Q system. Because if I rotate the quantum Q system, if you look, the quantum Q system has elements which are in the same cluster. So these elements are in the same cluster, they Q commute. But these elements, they don't Q commute at all. They satisfy some complicated relation. Nevertheless, I can write down this relation as a relation in the algebra. And I want to ask, what is the algebra generated by these elements, which are not, they don't commute? Okay, so this is the miracle. So it's not the cluster algebra that's written down over there, but the variables Q, A, K are still all polynomial in this bottom row. I can't make a cluster algebra argument for this. I can just compute the polynomials. And, okay, so in fact, I know the polynomials. One form for them is a quantum determinant. So what is a quantum determinant? So at this point, it helps to start using shuffle algebras, but we'll skip that because he says I only have a quarter hour left. So you define the current. So we start working with currents. So we have currents going this direction, okay? So this is Q1. U is the generating function for all the generators on this line. And I'm going to call this Q of U. Is this okay with everyone? It's just a way of collecting notation. And there's a product, this product, which I'm going to call the Q van der Mond product. It's somebody's Q van der Mond product. You can write QA of U as the constant term in all the U's of the product of A Q's times this Q van der Mond in A variables. Delta function is the physics delta function. And constant term just refers to the coefficient of U to the 0. Okay, so this is, if you write this down, just a Q deformation of the determinant. It's a particular Q deformation. So did I give an example? Yes, I gave an example. For example, for A equals 2, this is just the quantum Q system, I claim. And for A equals 3, you write this down. This is it has 7 terms instead of 6, which means what? Anybody? Thank you. So yeah, you can write down the quantum determinant in terms of alternating sign matrices. So that's how many terms it has. Okay, so that's in general true. Okay, so I don't have a proof in terms of cluster algebras, but I have a proof in terms of I have an explicit relation. Also, this is again an discrete integrable system, so I have a finite number of generators. I have a linear recursion relation, and the conserved quantities can be beautifully written in terms of the same type of shuffle algebra notation. You take the quantum determinant, and so this is the analog, the Q analog of a determinant with defects. You introduce a defect here or here. So the denominator there, J, has to do with the jth conserved quantity. Okay, so those are my conserved quantity. Everything is really beautiful when you write it in this way. And so the algebra AG is finitely generated as a polynomial algebra by 2R plus 2 generators. Okay, I want to get somewhere. So what is this algebra? And so I have two relations that I know about this algebra. So I'm going to use as generators this bottom row. So the Q1k. I'm going to take z to the k and make a current out of this. Okay, these are my generators. And so they satisfy Q commutation relations when they're in the same cluster. Only neighbors are in the same cluster. They satisfy the quantum Q system otherwise. And so from this, for example, I can get Q2 from Q1. But in general, they satisfy this exchange relation. So they don't commute, but they have this beautiful commutation relation. And you ask yourself, I don't know what this is. So these are Q commutators. I don't know what this is, right? And I say to you, you do know what this is. Okay, so first of all, how do I prove such an exchange relation? If you plug in m equals, so you do an inductive proof. If you plug in m equals 1, this is just the exchange relation. If you plug in m equals 2, it's just two applications of the quantum Q system. But if you plug in m equals 3, you get a mess. So you don't want to prove it that way. So you use the fact that this is a discrete integrable system. You use this fact once again. And so you define phi mn to be this Q commutator. You want to show that phi mn is 0 for all m. So you know it's true for m equals 1 and 2. And then, so you have to prove this, but the conserved quantity C1, it acts as a discrete Hamiltonian on Q1s. That is, it translates. It's a translation by one step k. Okay, so we have a Hamiltonian. We just act on this phi mn by this Hamiltonian. Okay, and we get the next one is equal to 0. We take the commutator of h. Okay, that's really easy if you know that you have conserved quantities. Okay, so still, here's my claim. This funny-looking relation is just this relation when written in terms of generating function. So, okay, does anybody recognize this exchange relation? So this is it's the relation in U n of t inverse, and it's not Q, it's square root of Q. The subalgebra of UQ SL2 hat. U square root of 2 f SL2 hat. Okay, there are reasons for this. It's because there's an elliptic whole algebra hiding behind this. But this is what I want to say. So the quantum Grothendieck ring is equivalent to the universal enveloping algebra inside U square root of 2 of SL2 hat. This is the relation that the currents E satisfy. And so the theorem is that my algebra AG, curly AG, is a quotient of U square root of 2 of N of hat, U plus this algebra, by the quantum determinant relation that I have because the n plus first line is 0. That's my theorem. So it's not the quantum affine algebra, it's the quotient of the quantum affine algebra because I have finite rank. So I have not seen this algebra in this room before, but this is what I get. Okay. So I have to hurry? Okay. Okay, so the other thing I want to say is, so it's very important that I started out by talking about graded characters, symmetric functions with coefficients in z of q. And these symmetric functions, so consider the set of all such symmetric functions. They form my set of characters. And I have a map which is insertion of another representation into the tensor product. So I had a tensor product. I want to put one more. So I'm not actually on the level of representations. I'm only talking about the level of characters. So I have, let's say, W1, W2, and then I want to add one more W here, right? I should be able to do that to my tensor product. And I'm asking what happens to the character when I insert one more representation into this functional. And what happens is, well, the character is just a symmetric function with coefficients in Q. There's some Q difference operator that acts on the character that gives me the next character that corresponds to this insertion. And what is this Q difference operator? And the Q difference operator is just this thing here, which I don't know in this audience anybody would recognize. this Q difference operator. So what it is it looks like a rational function, but it preserves the space of symmetric polynomials. And Q doesn't look like it's here. Q is hiding in gamma I. Gamma I acts by multiplication of all the z's in the set I, in the subset I, by Q. That's where the Q is hiding in this equation. It's a Q difference operator. So in general, such Q difference operators will not commute with each other because you have z's here and you have the Q difference, gamma I here. Any remarks at this point? Any guesses? So, okay, so the fact is that if this is really my generating, my Q difference operator, it should satisfy the quantum Q system. So this is a polynomial, so it's a polynomial representation of the quantum Q system. That is, these elements, DAK are a representation of QAK when acting on the space of symmetric polynomials. So if I look at these operators, I have to show that they satisfy the quantum Q system. That is, they satisfy the correct Q commutation relations, and they satisfy the exchange relation. So it's a polynomial representation of a cluster algebra mutation. Okay, the one thing which is easy to see is that D n plus 1 is equal to 0 because there is no subset of 1 to n with n plus 1 variables. Okay, so this is the easy part. These are kind of hard to show, and you use shuffle algebra type arguments to show this. Okay, but now to get on with life, I look at this operator, and actually, if you look at the 0th one, DA0, it's this operator. There's no. Let me remind you. Here I have a z to the k times this difference operator. If I remove z to the k, then this operator, DA0, they're just commuting operators. They commute for different a's. They're the t going to infinity limit of the Macdonald operators of type A, the Macdonald difference operators of type A. If I have, well, I have to renormalize them by the highest power of t that comes up. Okay, so then you look at these operators and you ask, well, what are the other operators? So I'm going to t-deform everything I said very quickly. There is a DAHA. Does everybody believe there's a DAHA? So it's generated by generators x, y, and t, and there's a polynomial representation of the DAHA on which x acts by multiplication by zi. And then the elementary symmetric functions in the y's commute with each other, act by the Macdonald operator DA0. That's for type A. And this action preserves the space of symmetric polynomials, and the eigenfunctions are the Macdonald polynomials. So this is, some of you know this and some of you don't, but it's true. Okay, now what are these other operators that I get? So the t going to infinity limit of this is the generators of my cluster algebra. So what if I put a z to the k here? What is this? So in the t going to infinity limit, I know which algebra these generate. These are Macdonald operators, but they're shifted by the DAHA always has an SL2Z action corresponding to exchange of x variables with y variables. And if you dig very deeply into Cherednik's book, you find out how to do this SL2Z action. So there's this operator in the completion of the DAHA. And if you act with the adjoint action of gamma to the minus k on your Macdonald operators, their representation is precisely this operator. That's my claim. And I'm not talking about the whole DAHA now. I'm just talking about the spherical DAHA, that is DAHA symmetric polynomials. Okay, so my claim is that the operators DAK, which in the t going to infinity limit goes to the representation of my Q system, are just the SL2Z translation of the Macdonald operator. Okay, so the algebra AG of Q and T, now Q and T deformed, is generated by, which is generated by these operators. M is the abstract operator, abstract algebra element of which DQT is a representation, is a subalgebra. So let's see. It's a polynomial algebra again. This is highly non-trivial. There's some analog of a QT determinant, but still we need to work on this QT determinant. So it is a polynomial algebra, and it is a subalgebra. It's not a quantum cluster algebra. It's not a generalized cluster algebra. I don't know how it relates to cluster algebras, because so it looks like this, but then it has lower order terms, it's not closed on these operators. I have to define a larger set of operators. Okay. So when t goes to infinity, you in fact get the quantum Q system, but then these lower order terms go to 0. Okay, but they do satisfy nice exchange relations. So I don't have a quantum cluster algebra. What do I have? And my claim is that I have the quantum toroidal algebra, which most of you will know nothing about, but some of you will. So the generating functions for these m's satisfy an exchange relation which looks like the SL2 hat exchange relation, except that you trade the function z minus qw to a product of 3 factors. And these 3 factors show up in the quantum toroidal algebra. They are responsible for all this excitement in physics, you know. Okay, I won't get into SUSIs and things like that, but n equals 4 supersymmetric string theory. This algebra controls all of this. And then the polynomial relation, which is it's a plus, but you can't see that it's a plus. This is a mn plus 1k is equal to 0. So the qt determinant of n plus 1 elements is 0. It generates some ideal, and the quotient by this ideal is my algebra. So my algebra is the quotient by the ideal that the n plus first qt determinant is 0. So when n goes to infinity, we just get usual Macdonald polynomials, usual Macdonald theory. We get everything is normal. Okay, so now for my advertisement. 1 minute? Okay, so if we return to this Q system for other types, okay, this was my quantum Q system for other types. Again, we have a linear functional from the product of the ordered product of solutions of the Q system to these graded characters for all other types, and we ask the question, okay, what are the difference operators in this? Because this is how we got our algebra, right? And so the claim is that, so what are the difference operators? What is the algebra associated with this? Like, where should we look for the analog of this correspondence between the deformed Grothendieck group and some algebra? And so, is there a current algebra and so forth? Here's one answer. Here's type Bn, which fortunately is the same type that David chose to talk about. This is D1n, okay? You can see it's a sum over the Weil group this time. So it's Weil group symmetric. So this epsilon can be plus or minus 1. So the Weil group for type Bn is Sn smash product with Z2. And so we're summing over n and the smash product with Z2. You get these because, so they're Macdonald type operators. It's not clear which Macdonald operators you should use. There's a Macdonald operator. Okay, there's a Macdonald operator for each node in the Dinking diagram. Macdonald wrote down these, I believe. They're not the right ones to use. Van Degen wrote down some operators which reduce in certain limits to the correct algebra. Okay, this is one of the ones that you get. The other ones are mostly QT determinants in this, except for when you get to the end here, for types B, C, D. Okay, so there are such difference operators. And so, for example, for type Bn, unlike David's statement, which is why I was curious, the algebra ABn is generated as a polynomial algebra by these D1n's, or Q1n's, however you want to call them, but spinor representation also. There's one more representation, which is not a QT determinant. So you need more generators for the algebra. So it's not going to be such a nice current algebra. Okay, Outlook, that's my conclusion. Okay, so we obtain a representation of the subalgebra of AG of the quantum cluster algebra associated with the Q system by Q difference operators. So we have a representation of a cluster algebra, or at least a subalgebra, and therefore the whole algebra by Q difference operators. We can construct graded characters with these, so we know that they're good. And for the other types, we get them as limits of Van Degen operators, and they're SL2Z translated version. So we know that we have some representation of the spherical DAHA. In type A, we had also the elliptic Hall algebra and the quantum toroidal algebra, and in the other types, this is a completely open question. But to see how all of this is done, I would like you to all be aware that there is a conference in Michigan, right, in 2 months from now or something like this, and Philippe will explain all of this there. So this is my advertisement. Thank you very much.